for the introduction. Hello, everyone. I'm Judy Hu from Johns Hopkins University. I'm very glad to be here to talk about our project on neonatal ASL. I have no financial interest to disclose. So I would like to start with briefly introducing the cerebral blood flow. So CBF refers to the amount of blood supplied to unit brain tissue. It plays a crucial role in supporting the metabolic demand during the rapid brain development of neonates. Well, a disruption of CBF can often indicate aberrations in disease states. For example, hypoxic ischemic encephalopathy is often associated with an upregulated CBF, while patients with perinatal stroke often receive insufficient perfusion. Well, there are many ways to measure CBF, including arterial spin labeling MRI and oxygen level PET, gadolinium-based perfusion imaging, as well as phase contrast MRI. So among these methods, arterial spin labeling MRI stands out for its stability in the neonatal application because it's first radiation-free, and it's non-invasive because it does not require any contrast agent ingestion. And also it can provide regional information. Even though ASL has been well established and extensively used in adults, its application in neonates still remains challenging. So let's first look at a representative CBF map acquired using Picasso in the neonates. And what you can see on the right are CBF map at similar level from an adult. We should be very familiar with an adult CBF map, right? So you can appreciate the relatively homogeneous CBF distribution with some nice gray and white matter contrast. However, the most striking feature of neonatal CBF map is the hyperintense signal in the deep brain region, spanning from the midbrain to the deep brain nuclei. The validity of interpreting these hyperintensities as real hyperperfusion remains questionable due to the rich presence of blood arteries within this region. Instead, macrovascular artifacts may account for these hyperintensities and therefore blurring the measurement of real perfusion. So a common way to eliminate this macrovascular signal is to use a longer post-labeling delay. However, even I didn't display here, we have tried to extend the PLD to 4 seconds, but it did not remove this hyperintense signal, which suggested that increasing PLD does not help. So this raised another challenge in the neonatal Picasso. We don't know what post-labeling delay to use because the arterial transit time of healthy, non-sedated neonates has not yet been systematically started. And we can also notice that the neonatal CBF map is suffering from very low signal to noise ratio. This is because the amount of perfusion signal we can get from neonates is bounded by their physiological limits. That is to say, they're having extremely low perfusion compared with adults. So how to enhance the SNR in neonatal ASL has been another challenge that we need to tackle. So with that, we would like to improve the overall quality of CBF measurements in neonates. So we would like to develop a new scheme to suppress the macrovascular signal in neonatal CBF map. And also, based on that, we can quantify CBF and arterial transit time in neonates, which can provide valuable information in determining the protocols to use in neonatal ASL. And of course, we want to enhance the SNR and reliability of neonatal Picasso. So we have proposed 2 macrovascular suppression schemes and compare them with a conventional 3D Grace Picasso sequence as shown in this diagram. So some excellent speakers has already explained the basic principle of ASL yesterday very well. So here very briefly, we label the blood that passes through the labeling gland and neck and trace them after they have entered the tissue compartment. But this is really ideal. In practice, right after the label module has ended, we have some unlabeled blood that soon take the place, and they will. Some of them will be concentrated in the log arteries at time of acquisition, and their contribution to the final signal intensity varies according to the cardiac cycle due to cardiac pulsation. And this will induce signal fluctuation, which we don't want. So we add an arterial suppression module in the conventional Picasso sequence, in which we apply a consecutive saturation pulse train during PLD immediately below the labeling module, labeling plan. So the signal from arterial blood will be attenuated. And another possible cause for the microvascular artifacts is the tail of the labeling bolus. So these label spin, for some reason, they haven't entered the tissue compartment at the time of acquisition. Instead, they are jammed in these large arteries, which will be very bright in our final CBF map. So we also want to get rid of this signal because it has nothing to do with the real perfusion. Therefore, we add additional flow suppression preparation module before the excitation. So this involved the use of bipolar pressure gradients within a tissue preparation to minimize the signal from fast-moving spins. We have tested these 3 sequences on 8 healthy term-born neonates. So during the scanning, the baby will retain in natural sleep without any sedation throughout the whole 1-hour research-dedicated scan. So this picture shows the experiment setup of our baby experiment. Just in case you cannot see, this is the small little sandwich that we want to image. So here shows the results. What you can see on the left are the group average CBF map acquired with the 3 Picasso sequences. And on the right are the temporal standard deviation across measurements. So we can see in the conventional Picasso CBF map that even with the 3 seconds PLD, a substantial amount of macrovascular signal can still be observable within the deep brain. But with the application of arterial suppression, these hyperintensities were greatly diminished. And this reduction was further enhanced by the additional flow suppression, yielding the most homogeneous CBF map. And on the other hand, the temporal standard deviation gives us clues on where the signal fluctuation is most prominent. We can see that the great pulsatile signal nicely delineates the trajectory of blood arteries, particularly the circle of Willis. And this signal fluctuation is also discernible at higher slices due to the smoothing effect of 3D acquisition. But with the application of macrovascular suppression, this signal fluctuation was evidently reduced. So what you can see here are the quantitative CBF and standard deviation values within the circle of Willis and brain parenchyma. So as you can see, compared with the conventional Picasso, the CBF values within the circle of Willis was reduced by 53% and 59% in AS Picasso and AFS Picasso. In contrast, the CBF values within the brain parenchyma did not alter much, despite still showing a statistically significant decrease. Regarding the standard deviation, both suppression schemes result in over 65% of reduction in the signal fluctuation within circle of Willis, while no obvious alternation was observed within the brain parenchyma. So based on this result, the winner among the 3 sequences, the arterial and flow suppressed Picasso, were then used for a multi-delay study to quantify CBF and arterial transit time in neonates. Another 12 healthy neonates were scanned, and 5 PLDs were acquired, ranging from 800 milliseconds to 3,000 milliseconds. So what you can see here are the group average perfusion weighted images at different PLDs. So we can see that, especially in the white matter, the perfusion signal first comes in and then faded out due to the T1 relaxation. And by using this PLD-dependent signal, can feed for the arterial transit time within 4 hand-drawn RIs, including the inferior and superior cortical gray matter, deep gray matter, and white matter. And the ATT was estimated using signal weighted delay, which gives us more robust value of NTD estimation. And CBF was also computed by fitting the signal to an ASL kinetic curve. And this table summarizes this ATT and CBF value quantified in our study. We found that the arterial transit time in neonates is slightly longer than that in adults by around 500 milliseconds, not substantially longer. And we also found that CBF within the neonatal gray matter is higher than white matter. We also noticed that a notable combination of short arterial transit time and high CBF value within the deep gray matter, which is consistent with a previous Australian label PET study. So now that we have measured arterial transit time in neonates, we want to take a step back to the single delay ASL because a single delay ASL is more practical and more time efficient from a clinical point of view. So we have chosen a PLD of 25 milliseconds. So now the problem is, how can we enhance the signal to noise ratio under a specific PLD? As I mentioned before, the amount of perfusion signal that we can get from neonates is bounded by your low perfusion. So there's an alternative way that we can improve the SNR, which is to reduce the noise. A common approach to reduce noise in ASL is to use background suppression. The idea is that we can suppress the signal intensity of background tissue, which is the main cause of the physiological noise, thereby allowing the perfusion signal itself to become more prominent. Well, right now, the conventional Picasso sequence use modest background suppression, which preserve enough amount of tissue signal. This is to ensure that the sign of control and label signals are consistent, and the magnitude of control is always greater than label. In this way, we can just simply take the magnitude of control and label, do a magnitude difference, and this will give us a perfusion weighted map as what is shown here. So intuitively, one might assume that the more we suppress the tissue, the more effective we can suppress the background noise. So this is what we want, very dark with minimal background tissue. But things are not that straightforward when it comes to dealing with the subtraction between control and label. Since the residual signal are so small that the sign of the signal become uncertain. But in this case, both the sign of control and label are flipped, and the magnitude of label is greater than control. So if you do a subtraction between control and label, you will get a negative value, which is not correct. You may say, in this case, we can just do label minus control. But there's also other case where this control and label signal are having inconsistent sign. So in this case, a magnitude difference will fail. So this represent in the image is a dark hole in your CBF map. So what we are doing is that we take the complex subtraction between control and label and use the magnitude of complex difference as our CBF measurement. And this will correct the error brought by the magnitude difference. So this will remove the constraint of maintaining enough tissue signal in the Picasso. This will remove the constraint of maintaining enough signal in the after the background suppression, and we can minimize the background noise as much as possible. So how does it work? We have tested the 2 background suppression schemes on so far 8 healthy neonates, and each sequence would perform twice in order to allow us to evaluate the reproducibility, and each scan takes 3.5 minutes. So what you can see here are the CBF map acquired from a representative individual. So we can clearly see that the improvement of signal to SNR, even in the cortical gray matter, and you can see a well circumscribed structure within the CBF map. And this nice CBF mapping is very reproducible with enhanced background suppression when compared to regular background suppression. So the sparks I show here are the scatter plot of CBF values between 2 runs. Each color represents an individual, and each dot represents a voxel. we can easily see that the result from enhanced background suppression is more clustered along the unity line when compared with the regular background suppression, which is more spread out. And we can imagine, which is also the truth, that the spatial correlation coefficient of enhanced background suppression is significantly higher than that of regular background suppression, underscoring a better reproducibility and reliability. So this brings us to the summary. We demonstrated that the AFS Picasso appeared to be the optimal in suppressing the macrovascular artifacts in neonatal ASL, providing the most homogeneous CBF map. And ATT quantified in our study was slightly longer than that in adults, but not substantially longer. And we also found CBF in neonatal deep brain matter is the highest across the brain. We demonstrated that the enhanced background suppression, when combined with complex subtraction, can improve the quality of neonatal CBF measurement. With that, I would like to thank my lab mates and thank you for your attention.